This section is on the law of sines, which shows a relationship between the angles and sides of oblique triangles. The law of sines is used in general to solve, that is, to find missing angles and side lengths for triangles with ASA information, AAS information, and it sometimes works for SSA triangles. Now here's an example of ASA. We have a given angle, side, and angle, and the point of this sketch is to show that with those indicated measurements, there's only one possible way we can put together a triangle, and ASA is in fact a triangle congruence. There's only one way you can do it. The same could be said for AAS. Now SSA sometimes works, sometimes doesn't. This is called the ambiguous case. We've got side-side angle where the angle is not included, and as we can see, using these measurements, we can get these 2 points to coincide in a triangle this way, but we can also get them to coincide down over here. We move these, so you can see we get two different triangles here, and depending upon our measurements, sometimes we get two triangles, or it's possible to get exactly one triangle, and sometimes you get no triangles at all. If, for instance, this side is too short, then it will never reach, no matter how you try to set these things up. That would be zero triangles. And so we'll look at that using the law of sines in a more symbolic way, how you get 0, 1, or 2 triangles. So now going on to the actual law of sines itself, which is over here. The law of sines states that if you have triangle ABC, angles A, B, and C, and the sides opposite, little a, little b, little c, then the sine of angle A divided by side A is equal to the sine of angle B divided by side B equals the sine of angle C divided by side C. So let's take a look again now at the proof of that. So what we can do is, here's a triangle, an oblique triangle. We show the height of the triangle. The sine of angle B is going to be, we look at this triangle here, and because this is an altitude, we have a right triangle here in blue, so sine B is opposite over hypotenuse, h over a. Now looking at the sine of angle A, we've got this yellow right triangle, and that's equal to h over b. We solve them each for h, and of course the height is not changed from one triangle to another. It's h is equal to h. So setting them equal to each other, we get a sine b is equal to b sine a, and therefore we have a over sine a is equal to b over sine b, or if you want to do it in a reciprocal manner, in the way I showed in the previous page, you could flip them over. And of course this could be extended simply enough for sine c over c, depending on where you decided to draw your altitude from. So there's your proof for your law of sines. Here again is a way to look at the ambiguous case. We have angle A, we have side B, and then side A is that length, and we notice that how we set it up, here it hits in one spot and in two spots, so we get our two answers. Now, if instead we make this shorter, a right triangle would be exactly 1. Skips past that. If it's too short, you get none. Or there's ways to get 1 if instead we make the angle a lot bigger, for instance, and then we make a longer, then we'll get one triangle that way. So 0, 1, or 2, again, with SSA, which is the most challenging form of this. So let's take a look at some ways to use this. So here's an ASA example. So for ASA, we expect to get one triangle because it's in triangle congruence. You're given the information 110 degrees, 30 degrees, and 4 is the included side. Notice this is not at all drawn to scale. That's not really the point. The point is here is just to get something visual to look at. So I label the angles on the sides. I know clearly it's easy to find angle C. You just simply subtract from 180 the other two angles and you get 40 degrees. Now that I have angle C, I can use the law of sines and say the sine of 30 degrees over B is equal to the sine of 40 degrees over 4. Solving this for B, I get 3.11 approximately. And then I can use the law of sines again. The sine of 110 over its opposite side A is equal to the sine of 40 over its opposite side 4, and I get approximately 5.85. So that's ASA. Here's an angle-angle side example, so the side is not included now. I've got 75, 50, and 3, but the work is substantively the same. So to find angle C, I subtract from 180 to get 55 degrees. And then knowing that this is 55 degrees, I can use the law of sines now and say sine of 75 over 3 is equal to sine of 50 over B. Solve this equation, you get about 2.38. Sine of 75 over 3 is equal to sine of 55 over C. Repeat the process, about 2.54. And of course, this is just the idea of solving this. You flip them over and you multiply by sine 55. Okay, now side-side angle. Let's look at 3 different cases: the no triangles, the 2 triangles, and the 1 triangle. So here we have if A is 4, B is 16, and A is 80. So again, I haven't really drawn it to scale clearly because the 4 is longer than the 16, but that's okay for now. I just want to have something to sort of look at. So I set up my law of sines. So I have sine of 80 over 4 is equal to sine of B over 16, and I solve this for sine B. When you solve it for sine B by multiplying by 16 and figuring this out, you get 3.94. So the thing to do would be take the inverse sine of 3.94, but of course that doesn't exist because sine being based on this unit circle, it will never be above 1 or less than negative 1, and 3.94 is too big. So this is a case where you'd see you're not going to get any triangles. So that's a 0 triangle case. Now let's take a look at a 1 triangle case. We have side 125, side 100, and then we have this angle 110 degrees. So using the law of sines, it's sine of 110 over 125 equals sine of B over 100. When I solve this for sine B, I get 0.75175. Now, taking the inverse sine, I would get 48.7 degrees. But the thing is, inverse sine evaluates in quadrants 1 and 2. So one angle is 48.7. The other angle, which would give you this sine value, is 180 minus 48.7. So maybe that angle works as well. Now let's see if that would be the case here. Well, that angle, 180 minus 48.7, if that indeed was the answer, I'd have to add it to 110. And when I do that, I get something which is bigger than 180. So I wouldn't have any angles, degrees, so to speak, left for my last angle. So clearly this isn't going to make sense. So there's only going to be one triangle. So the only value you've got to worry about is the 48.7. And then from there, you can continue on and use law of sines again to get the rest of this triangle. Now, let's contrast that with the 2 triangle example. So here we have A is 10, B is 25, A is 20. Okay, so using the law of sines, sine of 20 over 10, so sine of A over A equals sine of B over B. When I solve this for sine B, I get 0.855. Now, inverse sine of 0.855 gives me 59 degrees. So I drew 59 up here in my unit circle, noting that 121 is the supplement of that, and that would also give you a sine of 0.855. So we have this possibility too, or 121. Now, does either one of do these both work? Well, if I use the 121, I have 121 plus this original 20. That's still less than 180, which allows there to be 2 triangles because there would still be degrees left over for your remaining angle, angle C. So now I've got 2 cases. I have the case where B is 59 degrees. If B is 59, then C must be 101 because you do 180 minus 59 minus 20 to get 101. And then we do law of sines again to get side C. The other possibility is if angle B is 121 degrees, and so we subtract 121 and 20 from 180 to get another value of C is 39 degrees, and we do the law of sines again, and we get this possibility. So again, remember, this is based upon this idea of having 2 different triangles, which came about in this sort of case right here, where you got the larger one and the smaller one. So that's using law of sines to solve triangles. Now there's one other piece to this section, and that's the area of an oblique triangle. And this is if you're given side, angle, side information. Okay, this is for side, angle, side, and it gives you area of an oblique triangle. So it doesn't have to be a right triangle. So we start off with area is equal to half times base times height. So I've got this oblique triangle ABC. I draw in an altitude, and so I know that the sine of angle C is opposite over hypotenuse h over a, and therefore h is a sine c. So now my area will be 1/2 base times height, which is 1/2 b times a times sine c. Now you can just reorder the letters if you want to make it easier to memorize. So it would be half ab sine c. But of course this works for any side angle side triplet. So basically it's half one side the other times the sine of the angle in between. A couple of quick examples. So here we have a triangle. Side 6, side 10, 110 degrees is in between. So area K is half AB sine C, half times 6 times 10 times the sine of 110 degrees, approximately 28.19. This example here, angle's 120, sides rounded are 4 and 6, so half times 4 times 6 times sine of 120. Half times 4 times 6 is 12. Sine of 120 is rad 3 over 2 if you want to be exact. It is a reference angle, so it's 6 rad 3. One thing to note about this formula is that if indeed your angle is 90 degrees, so you actually had a right triangle, it would be 1/2 AB sine of 90 degrees. Sine of 90 is just 1, so you end up with 1/2 AB, which of course would be half times base times height, since we don't have a right triangle. So this ends up leading back to your right triangle area.